Hey Mark, I was having a hard time getting the sort of conveying my thoughts on email, so I'm making a quick video for you. I had a lot of this already kind of sitting around, so it's not too hard together. But um, so just as a little bit of background, as you know, when we talk about our mean maximal power curve, there's basically good data points in there, and then there's a bunch of junk data. And if you remember, the reason that happens is because really, when we do an effort, we kind of have this steady pace, and then we fail, and then immediately our power falls off. And so if we look at the instantaneous power from the ride, the instantaneous power data, you have your effort, you go to failure, and then you fall off, and then here's a longer effort, same thing, you pace, 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 hit your mean maximal power point, and then fatigue. But then what happens is when we're making our mean maximal power curve, or power duration curve, what we're doing is taking the mean power, and so when we average it, what happens is you get this pacing nose, hit your true point, and then you get these averaging tails afterwards that sort of cloud the issue of what's real and what's junk data. So when we look at what the MMP curve does is it kind of throws a line over this whole thing, and so it tells you that it makes you think, well, you have a bunch of good data here when really you only have these two true points. And to and you guys know this, that's why in Golden Cheetah you've got your algorithm to pull out the maximal points when you're fitting the critical power model, but there's kind of an issue that arises. So I wanted to kind of explore some of the effects of these. So what I did is I made a simulator that takes basically a model and runs a bunch of simulations of picking random durations for your efforts and then makes mean maximal power curves out of it. And you can see that when you do that, you get a bunch of different like stair steps and things like that. And sometimes you get these things that look like real physiology, and they're probably just not. So you can see the more true efforts that we add in, the closer it approaches the true model. And so, here's the true model finally revealing itself when we do multiple simulations. And so, like with the critical power model, the critical power itself is actually not that affected because you get kind of into the flat zone here, and because of that, it's fairly consistent. But you get these big gaps in terms of your W prime between what your true mean maximal power fit is and what happens if you just go ahead and keep this junk data in like Andy Coggan does. So that's good and bad. The reason it's good is because if we think about our pacing noses and averaging tails, this is what it does to the data. So if our true data point is here, the averaging tails and pacing noses basically has a skewed error where it skews all the data downward, makes it look lower than it is, and it's not Gaussian, it's kind of this skewed shape there. The problem that we have is then we've got error from the power meter itself. So if our true data point is there, and then we've got this plus minus 2%, and then we have kind of this Gaussian distribution. Now, if you just go ahead and do one test, you're probably not going to get thrown off that much just because it's just by probability, most of the time you're going to fall within somewhere in the mean. However, we introduce some systematic bias once we start selecting the best point of multiple tests. So if your power never changed, and we're just say this your 10-minute test, and you repeat it over and over, what happens is every time you throw an extra data point, you're always going to pick the higher one. And so you can see from one data point, it's going to be randomly distributed in Gaussian shape. Once we're picking between two data points, now we're always going to be biased high. Problem is, over the course of a season, if we pick multiple data points, or if we're picking from multiple data points, then we're going to be really biased high and potentially quite biased. So what my thought is that we can combat that a little bit by picking maximal points, but from multiple points along the data curve basically within a local region, picking out the best points. So that way we're not we're trying to kind of get the best of both worlds. What we're trying to do is eliminate this stuff here, but not get as biased by this effect here by keeping it to a relatively low number at anything. So what I mean by that is when we take the power duration curve and we plot it out on that log scale, it becomes pretty obvious where the low data points are because of the way that the average new tails pacing noses happen. So what I wanted to do is come up with the simplest way to kind of get rid of that junk data. And the first step in that is to go ahead and sample this so that it's consistent over a log scale, because that's when it's easy to see that. So the first step of that algorithm, all it does is sample, and you can see that, yeah, initially we don't have enough data points, so it's not perfectly uniform here, but once we get into it, this is a uniform sampling over a log scale. And now what that lets us do is use a real simple smoothing of just a running average to create a smooth data set. And so now here's the smooth, and this is just a 10-point running average. What you can see now is that if we overlay this on top of the true data, suddenly our submaximal data points all pop out. And this doesn't look like it's that dramatic, and part of that is because this data curve I specifically made with high quality data. I did a lot of tests at a lot of different durations, and but you can still see when you've actually sampled the data out. So what this algorithm did is it went ahead and said, okay, if the data point, the raw data is above the smooth curve, keep it. If it's below the smooth curve, get rid of it. And it successfully picked out all the trials that I actually did except for one. There was one trial here that it viewed as a submaximal data point and kept in all the actual efforts that I did. So if we're fitting now our critical power model, what you can see is that, yes, we're still picking the bests, but now we're picking the best from multiple data points instead of just the couple of data points that we had before. And one advantage of using the Ward-Smith model or an extended model is we can maximize how many points from the curve that we sample, so that way we minimize the effect of that bias that I was talking about. So effectively, instead of going and picking the best out of this, what we're doing is we're going to multiple areas along the data curve, so that we're picking the best out of say just a couple of we're picking the best one out of just a smaller number, so that way we don't get as much bias from the power meter noise. So this potentially can be useful for the critical power model, but it's going to be even more useful for the extended range models. And so I think, like, for example, on Damien's model, if you do use this algorithm and then just let his model fit, just do an OLS fit on that clean data, you're going to get some better data out of his model than picking the best data point from sort of ranges. Anyways, let me know if that makes any more sense than the emails. Hope it does.